Welcome to Sober Math. In this video, I will demonstrate how to calculate the depth of notches cut in two identical disks in order to get them to roll together smoothly when you interlock them. Although this video stands alone, if you haven't seen the Numberphile video entitled Wobbly Circles featuring Matt Parker, I highly recommend it, as I'll be adopting their wordage and notations here. I left a link, so do check that out. What did you think? Pretty cool, huh? The copper discs used for those videos were thin and approximated flat circles, but they do have some thickness. This suggests the question, what happens when you try to join thick discs? Today I build and discuss a thick disk version, show you how to make your own, show you how the depth calculation changes, some pros and cons of the thick wobbler, including a pathologically bad example, how the calculation reduces back to the circular wobbler in the zero thickness limit, and of course the derivation of the formulas to get the cut depth in the first place, because after all this is a math channel. This will involve more elaborate algebra than you saw in the Numberphile video, but that's the nature of this beast. Nothing terrible, just messy.
Hey buddy, I don't need the dissertation, just tell me what to do.
Hey, I got you. If you just want to make one, feel free and skip ahead. For those of you interested in the derivation, as a warning, I go slow on important details, but to save time I also breeze through the boring busy work, which I call crossing the desert, where there's no discernible landmark and we just want to get from A to B. Of course, if you are inclined and interested, please feel free to check my derivations. Are you ready? All right, let's get rolling. To start, I use two identical disks. Now important, they should be smooth and cylindrical. This will make it easier to measure the diameter and the thickness with a digital caliper. I bought these two from Michael's Arts and Crafts store. The question is, what is the appropriate depth of the square radial cut in order to interlock them? To find out, we can use versions of the two diagrams representing two stages of motion in the Numberphile video. Let's start with this edge-on view. So here, as before, we can label the radius r, but we have to account for the thickness. I'll call this 2a, so that a is the half thickness. Well, because trust me, notice that the disks interlock at right angles. Because of symmetry, each leans at 45 degrees. The tiny triangle, including the midline, is a 45-degree right triangle. It's isosceles, therefore this bit of dotted line has a length a. And then here we have the height h. So we extract this simpler diagram. This larger triangle is isosceles, so the other side is height h as well. Now we apply the Pythagorean theorem directly to get this, which simplifies. The height is positive by definition, so we take the positive solution. Now we put this little formula aside. So on to the profile view. These two blue dots represent the centers of each disk, which are a distance d apart. The middle one is the center of mass of the whole configuration, from which we get the height h above the table, which should be a constant of the motion, or at least the same in both stages. So we label the radius r here and here. Our half thickness is a, but this time we're not leaning at 45 degrees, so the segment on the lower left, we'll call it w. And then the center of mass bisects the line between centers, so we use d by 2 twice. And so get rid of the clutter and move this up. So how many right triangles do you reckon? Yep, there are 3, but we'll flip this tiny one over. So these 3 are similar right triangles, because they share one common angle at a common vertex. So let's label them. And this hypotenuse is missing a label, so we'll fill that in. Great. So what do you remember from geometry? Corresponding parts of similar triangles are proportional. These triangles scale to one another. For example, for the first and third triangles, we can write down this proportionality. And for the second and third, we can write down this one. So now let's clear the page and move these up. And now for the tedious work of solving the first for w. Don't worry, I'll speed through this one to save time. So we cross multiply, and then we square. Why? Well, we have to unearth that w under the radical. We distribute and then expand. We distribute again. And why is that? Well, I'm hoping for something to cancel. More than half the time it works. It turns out these two terms cancel. So they're out of here. So nothing else cancels, so we'll rearrange in common terms of w. So now we have it in quadratic form, in w. And then we solve for w by plugging these coefficients into the quadratic formula. All right, this discriminant looks messy. Let's see if we can simplify it. We expand factors, and then cancel this pair, and then this pair. Nice. Then we factor out that a squared, and then shove it back under the radical. So that's done. So moving on to the second one. So what do you guys reckon? We could solve this one for w, or maybe solve it for d. So I'll choose d. I'll explain in a moment. So we cross multiply, then distribute, then collect like terms in d, and we factor, and oh, we can factor again. Cool. Multiply out that 1/2, and then isolate d. So what do we have here? We appear to have a conundrum. To solve for the first one to get w, we need to know d, right? But to solve for the second one for d, we need to know w. So one standard method is to guess the value for d, plug it into the first equation, then use this value for w and plug it into the second equation, and then we find a new value for d. What's next? Right, we plug this newer d into the first one again, and then find a newer w, and then we repeat this process over and over until we get a convergence. And so we're looking for a value of d that matches the previous one. And when that happens, that's our solution. Amazingly, your initial guess can be terrible, and this process usually still works. So here's an example for a disk I'm using. You can do this method quickly on spreadsheet. You can type the two equations into two neighboring columns. In the next row, you can make your values dependent upon the previous row, and then just drag and drop. And then you can see this convergence. And here you can see my terrible starting guess. However, a lot of you might be thinking, why do we need 3 equations? Can't we just use algebra to plug one equation into another and then solve for d, and then get rid of the w entirely? Well, we can. And so here it is. As a kindness, I skipped all the pages of algebra to get here. So yes, it is messy, but it only explicitly depends on the radius and the thickness a, and also implicitly through the height h. So here's a challenge for you. It's not hard to show that as a goes to 0, this formula reduces to d equals the square root of 2 times r, just like the Numberphile video. So given a and r, we know what d is. But how do we make the cut? Well, the depth of the cut is given by this formula. So I took the liberty of plotting solutions for the d equation, and this is a quadratic approximation found on spreadsheet. Notice that when a is 0, we regain the fractional depth of 29%, as reported in the original Numberphile video. For some strange reason, the disks cannot have a thickness bigger than 41% of the diameter. Otherwise, d is less than 0, which is impossible. When we get close, like this plot, the center of mass is directly over one of the contact points, making the roll unstable. It isn't hard to imagine where the equal height requirement might break down in actuality, which invites the question, perhaps the 2 stages aren't enough to ensure constant height for this structure, unlike that presumed for the circle wobbler. Did you hear that repeated clacking sound? And did you notice the wobbler slowed down? What's going on? Better check the smaller one. It's louder this time, and it's slowing down. And reversing. What's going on? Upon a little reflection, this clacking sound is no more mysterious than that of this board rocking on the ground, which the cross-section of each disc periodically does when upright. Energy is being dissipated with each clack, and so the rolling motion slows. By contrast, the circle wobbler will travel further before friction slows it. Then again, that small cross-section can easily deform under torsional stress, and the wobbler won't get very far. Let's build this thing. You'll need to mark 2 pivot points very close to the edge of the disk by about a millimeter on opposite sides. They don't have to be exactly opposite. As long as you choose the appropriate radius on the compass to mark 2 arcs that overlap inside the disk, you're okay. From there, you can draw a diameter across the disk. This will be the midline of the notch. From the edge, mark the notch depth from the formula I'm about to give you. Draw a perpendicular line at this depth. Draw 2 parallel lines, each a distance a from the midline. Both terminate at the perpendicular line. For a wooden disc, if you're using a jigsaw, it might take a few successive curved cuts to get that nice squared notch. But let's get you that depth value for your discs. You just need to do a little arithmetic. So step 1 in calculating the depth of your notch, pick your measuring units. So measure the diameter. I recommend using centimeters, measured in the nearest tenth of a centimeter. It's metric and you don't have to convert anything or play with fractions. Divide this value by 2. This is the radius r. Next, measure your thickness. Make sure the units are the same. I recommend using a digital caliper, and a precision of 1/10 of a millimeter is probably good. So divide this thickness by 2. This is a. Divide a by r. Call this number x. It's a ratio, so this number won't depend on the units, assuming they're the same. You are going to plug x and r into this quadratic approximation to calculate the depth.